Is that making sense what I'm saying there? For the practice exam, number 10. Okay, let's go look at those harder ones. Yeah. Yeah, and you can just leave it just like it is. That's totally great. Yeah, just write remainder. Or you just leave the 14. I'm happy. I'm really just looking for this. This is great. I'm very happy if I see that. Good on that? Here, so it says LC. Now, didn't we do 16 earlier? And then I didn't do the rest, I think. Let's do the rest if we have time for that. So we already did. So I'm going to start with B. LCM goes into AB. So LCM of AB goes into AB. Is that what it says? Yeah. So there will be, I think there's one or two, I think there's two questions on the exam that have parts A, B, C, D, true, false, kind of like this. So they're each 1 point. So it'll be two of them, so 8 points. So 4 and 4. So it'll be 8 points. It'll be questions like this. So and I won't ask for reasons. They have all these true because, false. I'm just going to say true or false. You can totally. It's all you need. It's true. It'll be right, true or false. So how do we know if that's true or false? Well, I suggested last time, just make up some numbers. Because basically they're saying that the LCM, what's that straight line? Divides into kind of like that. If you want to make long division just to keys your memory better. Divides into A times B. They're saying, is that true for all numbers A and B? Is that true for all numbers? Could you put anything in there and that's always true? I think it is. Let's see. So pick up any numbers you want. How about nice easy ones like A is 2, B is 3. So I think, okay, the LCM of, not A and B, it's 2 and 3. 2 and 3. Does it divide into 2 times 3? Why am I doing times? Because this is A times B, isn't it? They're right next to each other. So that means multiply. Everybody with me on that? A, B right next to each other means multiply, doesn't it? Like in algebra, X, Y, A, B means times. So that's going to be 6. So we're saying, does the LCM of 2 and 3 divide into 6? Well, I don't know. What is the LCM for 2 and 3? How do you find the LCM for 2 and 3?
They're already broken down to their primes, so just 2 times 3 is 6.
Good job. Exactly. It's already primes, right? It's already primes. Remember the rules we've learned for LCM? That LCM, so the first number's 2, the second number's 3. Remember, you give each one their own column, right? And the LCM, you take the greatest. Remember how it's opposite? The least common multiple, you take the greatest of each prime. And the greatest common divisor, take the lowest of each prime. So what's the greatest amount of 2s? What's the greatest amount of 3s? 2 times 3 is 6. The LCM is 6. And that makes sense, huh? If you had a couple... LCM is like LCD. Remember fractions from your algebra days? If you were adding a half and a half and a third, what would be the common denominator? 6, right? That's all LCM is common denominator. So it would be 6. Does 6 go into 6 evenly? Well, yeah, perfectly, one time. So it worked for 2 and 3, therefore it works for every number. No, that's not good logic. But probably, that would give you a clue that, yeah, this is probably true. Now, how do you know for sure, for sure? Well, you could try some more numbers, but you only have so much time, So I might, if you had, I'd probably come back to these. This would be one of the ones, by the way, when you take a math test, or any test really, it's always best to do the ones that are easy for you first. Do the easy ones and come back to the ones that give you trouble, because you don't want to get stuck there. You don't want to get stuck on something that's giving you trouble and waste a whole bunch of time and then not get on to the ones that you could have easily gotten if you had enough time, right? So when you take this test on Wednesday, in case, for many people there'll be no trouble with time, but for some there may be. I'm sure there will be for some. Just go through the test, do all the ones that come quick and easy for you. Get those all done, and then go back to the ones that were a little more trouble. So like I might circle yes or true, I guess it's true at this point, and just go on with the rest of the test. If I have time at the end, come on back and try a couple other numbers, but it's probably going to be true. It came out true this time, and I just picked random numbers. It's probably always true. It is always true. I don't know if you can feel it at all. Do you feel the truth of it? The LCM is the container. That's always going to fit into the entire numbers. That's always going to work. Everything's going to go into the two numbers. A times B is like the whole of A and the whole of B put together. So yeah, the LCM is going to go in there, the GCD is going to go in there, everything's going to go in there. It's the whole thing. That's going to be true on that.
For
Yeah.
the student class, problems, can you just answer, or do you want us to show it work?
Oh yeah, I don't care. Yeah, do whatever you want. I won't even be looking at your work. Just the true false is. Well, I might look at your work if you wrote like this, and then you said false. I don't know. I might give you partial credit. I might go, oh, they knew. They just messed up at the last second. I don't know. Of course, they're only 1 point, so I can't really get partial credit on the true false. So yeah, maybe not. So yeah, show me your work. That way, I can give you partial credit if you just add wrong or something silly. Okay, so we could do C. C. Let's try that one. GCD is less than or equal to A. So 16. C. GCD less than or equal to A. So go ahead, just pick some numbers. Pick A, pick B, and just see if it works for the numbers you pick. If it does, it probably works for all the numbers. Maybe not. How about I pick 10 and 12? You probably should, by the way, pick a couple. 2 and 3 wasn't the best way for me to go, because you want to pick a couple numbers that have something in common, something not in common, That way you're kind of covering a lot of bases, 2 and 3 were two unique primes. There could be weird stuff that's true for them that's not always true. You know what I mean? But a number like 10 and 12 have a little bit in common, like 2 goes into both of them. They have a little bit not in common. This guy has a 3, the other guy has a 5, and they don't share that. So they have a little bit in common, a little bit not in common. It's a good pair of numbers. So if you're looking for a pair of numbers to pick on a lot of these problems that aren't too hard, but still probably will tell you the truth right off the bat, 10 and 12 would be a good pair. I'm not sure I'd do 2 and 3, because they're two kind of unique primes that might not always tell the whole story. They might be true when other things aren't. So anyway, I'll try 10 and 12. Is that less than or equal to 10? The first number, I made the A. And it doesn't matter, you can switch them or whatever. So is that true? Is that true or is that false? Well, what's the GCD for 10 and 12? How do we find GCD? Well, we do the prime factor thing. 2, 5, what's 12? It's 3 times 4, 2, 2. So 10 is 2 times 5. 12 is 2 squared times 3. We good there so far? And the GCD, not the GD, the GCD, I'm just doing the prime factorization method. Remember how to find a GCD for two numbers? So it says greatest, but we actually do lowest, right? It's the greatest in common. I mean, Jose was a quarter. So how many 2s do they have in common? Just 1, 2, taking the lowest. How many 3s do they have in common? None. Because they don't both have 3s, so they have no 3s in common. How many 5s do they have in common? None. So you take the lowest number of 2s, the lowest number of 3s, none. The lowest number of 5s, none. So it's just 2. Is that making sense? So remember, for GCD, greatest, we take lowest number of 2s, lowest number of 3s, lowest number of 5s. It was just the opposite for LCM back over here. I took the greatest number of 2s, the greatest number of 3s. Huh? All right, anyway, so the GCD is 2. Is 2 less than or equal to 10? Right, that's the GCD. Yeah. Looks true. Looks like it's true. And you feel that it is always true? Right? If something is in common to 10 and 12, it's always got to be smaller than either number. If it's in them, it's got to be smaller than them. Right? If it's the GCD, 2 is the number that goes into 10 and 12, huh? So if it goes into 10 and 12, it's got to be smaller than either 10 or 12. That's always going to be true. Does that make sense? These seeming easier, not so mysterious now? So how about we move on? That counting number divisible by numbers 4 through 10. So 21. Smallest number divisible by, part A, 4 through 10. Okay, so remember how this works? Did you catch this from last time? You basically write those numbers out, 4, 5, 6, 7, 8, 9, and 10. The numbers 4 through 10. And I want to build like a bigger number that all of these numbers go into. So I want to build a number. I'm going to build it out of their primes. I'm going to take all these numbers and I'm going to break them down to their primes. So 4 is 2 times 2. So that's 2 squared. 5 is just 5. 6 is 2 times 3. 7 is just 7. 8 is 2 to the third power, right? 9 is 3 squared. 10 is not 2 squared, but 2 times 5. So I've got the prime. It's always about primes, isn't it? So we've got the prime breakdown for all those numbers. And now how do you build a number? Remember, you take one of each prime type to the highest power. I made an analogy like I'm going to go to the store today and I'm going to buy one of everything and I'm going to buy the most expensive one of everything. So I'm going to go into the store, I'm going to go into Save Mart and buy the most expensive milk they have. Just one. I'm going to buy the most expensive cheese they have. Just one, and etc. Right? One of everything. The highest power one. So, all right. So so I'm going to take 2s. Am I going to take, what's the highest power 2 you see anywhere? Right there, 2 to the third. So notice I'm not adding up all the powers. I'm just taking the biggest power I see anywhere. 2 to the third. Next, I got to take a 5. Do we see 5 squared anywhere? No. So just 5. And so I'm just going to cross them off as I go. Got 2, got 5, got 2. Need a 3? Is there 3? Is there a higher 3 anywhere? Yeah, 3. Am I going too quick? Everybody see what I'm doing? I'm just starting here on the left. I'm just saying, grab 2s. What's the highest 2? 2 to the third. Boom. 5. What's the highest 5? No, just regular 5. 2's are gone. 3. What's the highest 3? Looks like 3 squared. Done. 7. What's the highest 7? Just regular 7. Done. 2 cubed, already got 2s, already got 3s, already got 2s, already got 5s. There it is. Whatever that number is, that's the smallest number because he has just enough. So they all would go into him, huh? Do you see how we formed that? He has just enough. He has all the pieces needed so any of these guys are found in him, aren't they? You see what I mean by that? Like if I said, hey, where is 3 squared? It's right there. Where's 2 squared? It's inside that 2 cubed. Where's the 7? It's right there. Where's 2 times 5? There's a 2 here and a 5 there. And on you go. See how that's the smallest thing that contains all their pieces. So they would all fit in, huh? That's the smallest number they'll divide into. So whatever that is, I have no idea. And you can just leave it this way. I'm fine. Just leave that on the test. You don't have to multiply it out. Just leave that. Whatever that is. 40. I don't know. Some big number. Does that make sense? We good on that? Okay. How about 20? A little more systematic. Basically, if you want to, here's 22. If you want to find the smallest number with how do they put it? Let's go, smallest number with, I don't know, 10 divisors. Let's just do 10. 10 divisors. You want the smallest number with 10 divisors. Well, what do you do? Let me give a game plan. Yeah, and that'd be better. I didn't really do that last time. I was running out of time. Number 1, write all the ways to multiply to equal 10. So what are all the ways you can multiply and get 10? 1 times 10 and 2 times 5. Huh? Good so far? So you could write this right on your 3x5 card if you want. You know, anything you want. Both sides of a 3x5 card. Step 2. Subtract 1 from all numbers. So I'm going to go subtract Subtract 1, subtract 1, subtract 1, subtract 1. What do I get? 0 by 9, 1 by 4. So I didn't really write all this out last time. I kind of talked it out and reasoned it out and showed you 1 or 2 in 3 minutes, and we were out of time. So this would be the step-by-step systematic method for doing this. So write all the ways to multiply 10. 1 times 10, 2 times 5. Subtract. Why am I subtracting 1? Because the power adds 1. So I'm reversing it. You'll see when we're done. I'll run it back and it'll make some more sense. Now, step 3. Put P, Q, R, etc. under the numbers. So I'm going to go, this is P to the 0. Well, here, let me just do it right here. P to the 0, P to the 9. Oh, no, it's supposed to be P and Q. P to the 0, Q to the 9, P to the 1, Q to the 4. Right, so we have P to the 0, Q to the 9, P to the 1, Q to the 4. Those are our models or templates. Those are our setups. How about that? Those are our setups. That's the format we need. So put P, Q, and R, etc. under the numbers. And then step 4. Put in smallest primes to biggest power. Smallest primes to biggest powers. Because remember, you're trying to make the smallest numbers you possibly can out of these things. Put in the smallest primes to the biggest power. So as I look at, oh, and by the way, what's anything to the 0 power? Do you remember that? Yeah, anything to the 0 power is just 1, so you can just get rid of that. That's just 1 times q to the 9th, meaning it's just q to the 9th, huh? So you always get rid of the one with the 0 power. So our 2 templates, our 2 setups are any prime to the 9th power, or any prime to the 1st times a different prime to the 4th. Both those setups will end up having 10 divisors. Why? Because remember, you add 1 to the power, right? No, let's finish it off. So what's the smallest thing I can put in here? 2 to the 9th. 2 is the smallest prime, right? And what's the smallest thing? Should I go 2 to the 1, 3 to the... Because 3 is the next smallest prime. But I don't do it that way, do I? Why is that not the best way? 2 and 3 are the smallest primes. So why was that not a good way to do that? So I'm trying to make this as small as I possibly can. I got to put 2 primes here. Some prime to the 1st power, some prime to the 4th power. I'm going to use 2 and 3 for sure, because those are the 2 smallest primes. What's a better way to do that? Because that would be, whatever, 2 times, it'd be like 162, I think. Switch them, huh? What's that? Yeah, it'd be better to make the q be the 2. Is that what you're saying? Yeah, absolutely. Yeah, you want to swap them. Because not that way, because that'd be the number 162. It's way better to put the 2 to the 4th power and the 3 to the 1st. Right? You put the smallest prime, the 2, to the biggest power. Huh? Because that'll make the number smaller. What is that? And we're trying to make the smallest. Remember, that's what they asked us from the beginning. Find the smallest thing you can that'll do this. So I'm making it as small as possible. So that'll be 3 times 16. That'll be 48. So our 2 candidates for election here, 48 came out of one setup. And 2 to the 9th, what is that? That's 512. Came out of the other setup. So clearly 48 is way smaller. He's the smallest number that has 10 divisors. How do I know 48 has 10 divisors? Well, remember how we found divide? If we wanted to do it, we'd put a 1 here and a 1 here. Remember what we would do? And then you go 2 to the, so you go 2 to the first, 2 to the second, 2 to the third, 2 to the fourth. And then up here you go 3 to the first. That's all there is. All right? See how many boxes there would be there? 2 by 5. There'd be 10 boxes, wouldn't there? There'd be 10 divisors. I'm not going to find them all. But there would be 10 divisors there. Because you take each of these powers and you add 1 to it, huh? And that gives you the size of your array. So you see how I just kind of thought that backwards in my little steps here? I just said, well, if you get the size by adding 1 to the powers, then we should just subtract 1 to find out what those numbers are. That's all that method is. It's just walking you through the thinking them backwards. How are we doing on that? Is that making sense?
Can you go back to the questions?
Yeah. Find the smallest counting number that has, and I jumped down to J. I just did J. Want to try I? 9? Let's see. So 22I. So smallest number with 9 divisors. Find the smallest number with 9. So go through the reasoning. Start off, first write all the ways to multiply to equal 9. That's step 1, right? So step 1, what are all the ways to multiply to equal 9? So what times what is 9? Always do the 1 first. 1 times 9. And what's the other option? 3 times 3. And that's it. Step 2, subtract 1, right? Subtract 1. Subtract 1 from all. Zero by 8, 2 by 2. Making sense? Now what do you do from there? Step 3. You put the PQR under. We don't need R. Just P and Q. So this will be P to the 0, Q to the 8, and P to the 2, Q to the 2nd. Those are the two setups that'll produce primes, that'll produce numbers that have 9 divisors. Get to there. And now, stick in the smallest primes you can. So put in smallest primes to biggest powers. So, and the 0 power, that's gone. That's just 1. Anything to the 0 power is just 1. So we skip that. So put in the smallest primes you can to the biggest powers. So this one, first off, 2 to the 8th, which is some really big number. 128 or something? 256. Oh, 256. Thank you. And then the other one, what are we going to do for this guy? Oh, they're both second power, so it doesn't matter which one goes where. 2 squared, 3 squared. If one of them was a bigger power, though, I'd put the 2 in there and the 3 in the smaller one. What is that, 4 times 9, 36? So clearly 36 is the winner, huh? It's not even close. So we're finding all the different models and the setups and then take the overall lowest. 36 is the smallest number that has 9 different things that go into it. Is that method making sense on that? We got 2 minutes. No, it ends with a 5. I mean, that's just dumb. That one's just obvious. But what if I gave you a harder one? What if, and it's going to be random, so you know, the test, it's not going to be that dumb. What if I said, let's finish with this. Is, I don't know, 397 prime. Sure looks prime. Is it? How do you know if a big old number like that's prime? That's right. There'll be one of these, I think. True? There's just one whole question all by itself. I can't remember. There's definitely this question on there. I don't know how much it's worth. What do you do to check if a number's prime? To be sure. Remember we learned you have to check other primes. You don't have to check like all the numbers. And you check up to what number? How far do you have to go? There's like a ceiling on it. We have a roof. How far do we have to go? Square root. Yeah, somebody, isn't that 20 point something or other? 19? Is that 19? Is that what the square root of 397 is? Somebody have it in their calculator? 19 point something? So we just have to go up to 19. So that means you got to check 2, 3, 5, 7, 11, 13, 17, and 19. Just check those on your calculator. Try dividing by 397. If none of those go in, it's prime. If any one of those goes in, it's obviously not prime then. Something else divides it. So check those. Does that make sense? How to be sure? You just go up to the square root of the number. All right, it looks like we're at time.